Okay, so we have circuits with a battery, circuits with a resistor. Now we also studied capacitors. Now let's see what happens when we have a capacitor in the circuit. Let's start with the simple one. Let's assume that capacitor and the resistor. Initially, we charge the capacitor. So this is our circuit. Now, when we have the capacitor, there's also another thing we have to determine. And before, when we didn't have the capacitor, we were already kind of first choosing the positive and negative sense of the currents. Now we have to also determine the positive and negative charge of the capacitor. When will we say that the capacitor is positively charged? When we will say that the capacitor is negatively charged? Again, that is arbitrary. I will say that the capacitor is positively charged if this plate is positive, this plate is negative. And if the plate on the left is negatively charged, I will say that the charge of the capacitor is negative. That is just a convention again, just a choice of positive and negative. If you review our discussions on capacitors, we always treated the charge of the capacitor to be positive, the charge of the positive plate. The capacitance was positive, the potential difference was positive. We didn't pay attention to the signs. Now we have to pay attention to the signs. And okay, this is the positive plate, this is the negative plate. And let's just assume that the current, I will call the current to be a positive if it is running in this direction. This is again just a choice. I'm not saying that the current is running in this direction. I'm only saying that if the current is running in this direction, I will call it a positive current. If the current is running in the opposite direction, I will call it a negative current. That is the only definition this is a definition I'm making. A, B, C, D. Now we just use the Kirchhoff's loop rule. The potential from A to A, which we can write as from A to B, from B to C, from C to D, and from D to A. So what is the potential difference, potential drop from A to B? 0. Potential drop from B to C? Minus I times R. Potential drop from C to D? 0. Potential drop from D to A? Let's say the capacitor has a charge Q at this instant, and it has a capacitance, well, C. So the potential difference across the capacitor, if you remember, delta V was equal to C times V. Now, Q was equal to C times delta V. This is the equation for the capacitor. So the potential difference is Q over C. Is it positive or negative? That is the thing we have to pay attention to. Is it positive Q over C or negative Q over C? And remember, if Q is positive, it just means that this plate is at charged positively, the other plate is charged negatively. The positive charges create a larger potential than negative charges. So this plate should be at a larger potential than this one. So as we go from D to A, the potential is increasing. So the potential drop is minus Q over C. Now, any questions up to here? Or we find that I times R plus Q over C, this is equal to 0. Now, we have these two unknowns. We don't know I, we don't know Q, and we know that if we connect the capacitor, the charges from the charge will just flow so that it will neutralize the plate. So there will be a current running through this resistor. Well, let's just call it R. And Q will be time dependent. Q will change in time. Well, since Q is changing in time, I should also change in time. So we are talking about time-dependent quantities. That's what we are interested in now. In the previous example, there was no time dependence. But now when you put the capacitor, things become time-dependent. Because as the battery is being charged in time, the potential across the battery is changing in time. So things will become time-dependent. And the second thing is, how do we relate these two unknowns? So this is one equation that we obtained from the loop rule of the Kirchhoff. Now we have these two unknowns. How do we find the second equation for these two unknowns? Now, how did we define I? I was equal to dq over dt, right? So this was basically, if you wait this amount of time, dt amount of time, there will be this much current running through any given point or running through the circuit. Now, to fix some signs, let's say that dq is positive. Now, if dq is positive, there is this much charge moves from this plate to the other plate. How much does the charge in the capacitor changes? Does it increase by dq or decrease by dq? So you see, there is this current running through my circuit. Okay? And I know that if I wait dt amount of time, through this point, the charge that passes through this point will be dq in this direction. The charge passing through this point will be dq in that direction. And the charge passing through this point will be dq in that direction. And the charge passing through this point will be dq in that direction, because the current is the same throughout the wire. But that means if dq is positive, the charge in the plate is also increases by dq. So large Q goes to large Q plus small dq. So what we call dq over here is in fact the change in the charge of my capacitor. This is the general definition. Now we relate this dq that passes through my circuit to the change in the charge in my capacitor. So if dq is positive, then my capacitor is charged. The charge in my capacitor also increases by the same amount. So this is my relation between I and dq. I and the charge in my capacitor. Another way of looking, the problem was, how do we determine this sign over here? Should I be dq over dt or minus dq over dt? But you see, if I is positive, then the charge in my capacitor is increasing, so dq over dt is also positive. So there shouldn't be any sign there. If I is negative, then dq over dt, the charge in my capacitor is decreasing in time because the charges are positive charges are flowing in the counterclockwise sense. Then I should have included the minus sign. Now, if I is negative, dq over dt is also negative, so again, there is no sign over there. So I can just put that equation, put that relation in the previous equation, and we obtain that R times dq by dt plus q over c, this should be equal to 0. Or dq by dt should be equal to minus 1 over R times C times Q. So this is the equation satisfied by the charge in my capacitor. Now the question is, what is Q? So if you look at this equation, it should be such a function that when you take its derivative, it should be proportional to itself. So that is the property of this Q as a function of time. Now, what are some of the functions that you know? Let's try them. Which functions do you know? You know polynomials, right? So if d by dt of t to the power n, this is equal to n times t to the power n minus 1, well, it doesn't satisfy that equation. Well, you know trigonometric functions, d by dt of sine of, let's say, omega t, this is equal to omega times cosine omega t. Again, it's not satisfied. What other functions are you familiar with? A to the power alpha t. This is equal to alpha times e to the power alpha t. Now that's the function we are looking for. And we see that, okay, this function is such that when I take the derivative of that function, I get the same function multiplied by some coefficient given over here. So if you compare this equation with this one, you see that alpha should be equal to minus 1 over RC. So Q of t, well, if I just put any overall coefficient over here, it is still satisfied. So Q of t will be equal to some a times e to the power minus 1 over RC times t. Now, if you ask me how do you obtain this solution without this trial and error, trying all the functions, there is no way. Well, in this case, there is a way, but in general, there is no way. This is just, solving differential equations, most of the time is just you try all the functions you know. Well, in this one, in the first order differential equations, you can derive them, but again, the trial and error is the most general solution. Now, let's see. At t equal to 0, we see that the charge is equal to A. So let's just define this as Q0. So this is the charge of the capacitor at the time t will be equal to its charge at t equal to 0, e to the power minus t over, let's call it tau, where tau we define at r times c, is called a time constant. Essentially, it determines how fast the capacitor discharges. You see, this is what we do to discharge a capacitor. If you just connect the two plates of a charged capacitor, it becomes discharged. Its charge just moves and neutralizes itself. And as a function of time, so if this is Q0, it just goes to 0 quite fast. The larger the tau, the longer it takes to discharge the capacitor. Well, that is kind of expected because a large tau means either you have a large resistance. Well, if you have a large resistance, the current will be small, so the charges will move slowly from one side to the other side. Or the capacitance is large. That means there's too many charges in the system already. So it will take a long time to discharge it completely, or both of them. Now, any questions on discharging this capacitor? Now, the next thing we will do will be our homework problem. How can you charge a capacitor using another capacitor? This time, let's also add the resistance. Remember, he had this hypothesis that in this system, if you start with one of the capacitors fully charged, the other one empty to start with, eventually the charges will be distributed. The potential energy stored in the capacitors will be smaller, and the difference is the energy dissipated by the resistor. So that was his hypothesis, and you will be testing his hypothesis in your next homework. But let's see how can we determine the time dependence. So if you want to calculate the power dissipated by the resistor, you need to know the current running through the system. The current will be changing in time, and so the power of this resistor will change in time. To calculate the total energy dissipated, you have to integrate the power over all possible times. But first we have to determine the current. What is the current? So what should be the positive plate of the upper capacitor? Which one do you like? The left, right? Left. Okay, the left. So this is positive, this is negative. Let's say this is negative, this is positive. So which, I don't know. I mean, I am free to choose which side I will denote to be the positive charge. Maybe eventually I will have a total negative charge in this capacitor, which will tell me that this plate will be positively charged. But these signs are just my conventions, sign conventions. What will I understand if I say that this capacitor is positively charged? I'm saying that if I find that this capacitor is positively charged, I will understand that this plate is positive, this plate is negative. If I find that this capacitor is negatively charged, I will understand that this plate is positively charged, this plate is negatively charged. That is how I will interpret my final results. What should be the direction of the current? I will choose the counterclockwise. I. Okay, let's start from this point. A, B, C, D, VAA, which should be equal to 0. This is equal to VAD plus VDC plus VCB plus VBA. Nothing that tells me that I should go one way around the loop or the other way around the loop. I can just go whichever way you like. Okay, what is the potential drop? And let's also call this charges. The charge over here is Q1. The charge over here is Q2. Okay, as I go from A to D, what is the potential drop? Q over C1. The potential across the capacitor is always its charge divided by its capacitance. Positive or negative? It's positive because I'm going from the positive plate to the negative plate. So the charge, this is positive. There's a positive potential drop. From D to C, well, it is I times R. What is the sign? It will be minus because the current goes from positive to negative. So as I go from D to C, I'm going to a larger potential, so it should be negative. From C to B, what is the potential drop? Well, the potential difference is always Q over C across a capacitor. It is positive or negative? The potential drop? It is positive. You see, I go from the positive plate to the negative plate, so there is a potential drop. If Q2 is positive, there is a potential drop. So the potential drop is just Q over C. And from B to A, the potential drop is 0. Now Q2 over C2. So Q1 over C1 plus Q2 over C2, this should be equal to I times R. Now I have these three unknowns. I don't know Q1, I don't know Q2, and I don't know I. I have to relate them somehow. Okay, if there is current running through the system, the charge Q1 will be changing, the charge Q2 will be changing in time. And let's say I will be dQ1 over dt, and I will be dQ2 over dt. Now the next thing is, will they be positive or negative? Let's say I is positive. If I is positive, the charge in C1, is it increasing or decreasing? If I is positive, Q1 is decreasing, which means the derivative of Q1 with time is negative. So if I is positive, dQ1 by dt is negative. So if I want to have this equality, I should have a minus sign. We just consider one particular case. I is positive. If I is positive, it just means it's taking positive charges from this plate and putting positive charges on the other plate. So the total positive charges in this plate is being reduced, right? So if I is positive, Q1 as a function of time is becoming smaller and smaller. So that is with time, if dt is positive, if time is increasing, the Q1, the change in Q1 is negative. So dQ1 by dt is negative, if I is positive. So to have this equality, I have to have this minus sign. Well, I can say, look at the second equation. If I is positive, is the charge in Q2 increasing or decreasing? If I is positive. You see, if I is positive, it just means there are positive charges reaching this plate and positive charges are leaving this plate. So the charge is also getting smaller. Again, if I is positive, dQ2 by dt is also negative. So to have this equality, I have to have the minus sign. Do you agree on the signs? Or you are lost? This one. Well, what I am saying is, let's say I is positive. Okay, first of all, do you agree that I should be either plus or minus dQ2 by dt? So the question is, how do we determine the sign? So let's say I is positive. Okay, although we know that in metals the current is due to the motion of the electrons, let's just forget about that for the time being. Let's treat the current as the flow of positive charges. They will be the same. So if I is positive and if I wait 1 unit of time, there will be I positive charges that flow through the circuit, right? So there will be the charge on this plate will increase by I, which is a positive number. And the charge on this positive plate will be decreased by I. So the Q2, initially if the charge in this plate is Q2, which we said that the Q2 is the charge in this plate, the charge in this plate in a unit amount of time has decreased by I. So Q2 as a function of time is decreasing. If a function is decreasing as a function of time, it just means that its derivative is negative. We started with assuming that I is positive. And we said that if I is positive, as a function of time, this Q2 is decreasing in time. So if I is positive, dQ by dt is negative. So for this equality to hold, I have to have this minus sign over there. That is why I add this minus sign. Do you agree? Okay, so let us look at the above equation. Rather than looking at this equation, let's take its time derivative. Now, if I take the time derivative, 1 over C1 dQ1 by dt plus 1 over C2 dQ2 by dt, this will be equal to di by dt times R. Well, dQ1 by dt, we had already determined that it was minus I. This is also minus I. So we find that the current as a function of time is equal to minus 1 over C1 plus 1 over C2 times I. Let's just call that combination 1 over C equivalent times I. Do you agree? Or di by dt is equal to minus 1 over R times C equivalent times I. Again, I is such a function that its derivative is nothing but itself multiplied by the constant coefficient. It's just like the previous example. And the solution will have exactly the same mathematical form. The current at the time t will be equal to the initial current in my system multiplied by e to power minus 1 over R C equivalent times t. This is I. Now we want to find Q1 and Q2. If I want to find Q1 and Q2, well, I know how Q1 and Q2 are related to the current. I know that dQ1 by dt was equal to minus I This was what we had derived beforehand. dQ1 by dt is minus I. We already have determined what I is. So this is equal to minus I0 times e to power minus t over, let's call it tau. Again, tau is this time R times C equivalent. Let's multiply both sides by dt and evaluate it from 0 to some final time t. This should be equal to minus I0 integral from 0 to t I0 times e to power minus t over tau. Now I0 I just moved out. dt. Do you agree? So the left-hand side is just Q1 of t minus Q0. Now this subindex 0 I just always use to denote the corresponding quantity at t equal to 0. Q1, 0. This should be equal to minus I0 times e to power minus t over tau divided by minus 1 over tau evaluated at t equals 0 up to some final time t. So this is equal to I0 times tau times e to power minus t over tau minus 1. So Q1 is equal to Q1, 0 plus I0 of tau e to power minus t over tau minus 1. And similarly, you see, Q2 just satisfies the identical equation. So the solution will also look identical. So Q2 will be equal to Q2 of 0 plus I0 of tau e to power minus t over tau minus 1. So these are our solutions. This one. At time t equal to 0, this is the charge of the first capacitor. If you just put t equal to 0, this just becomes 1. 1 minus 1 is 0. So this is 0. So this is the charge in the first capacitor. And at time t equal to 0, this is the charge in the second capacitor. These are the general solutions. I don't know what initially, in the general case, the charge in the first capacitor, the charge in the second capacitor, they can be arbitrary. Which one? This E. This natural logarithm. I mean, it's well, it's because of this property over here. It is this property. If you take the derivative of the e to the power something, if you take e to the power x and takes its derivative, then it's just e to the power x. That's the only function that has that property. So that's why we have the e.
So can we just remove the capacitor example from the beginning without writing it?
You mean
The whole thing?
the whole thing?
Would it be too much?
No. It might be too much for you. You're already tired after 2.5 hours. Okay, you see. Any questions on how we write this equation? Well, the Kirchhoff's rules, whatever your system is, it's based the same basic principles. You go around the loop, you write the potential drops or potential increases as you wish, and then around when you complete the loop, the sum should be 0. Whether there is a capacitor or no capacitor, whether you have many branches of wires or a single wire, it doesn't make any difference. So the principle is still the same. So we just go around this loop in this sense. So when we go from A to D, we are going from a high potential region to the low potential region. So the potential drop is Q1 over C1. And then we go from D to R, we are going in the opposite direction of the current. So if I is positive, we are going in the opposite direction. So we are going to a region in which the potential is increasing. So that's why we have this -1 over there. And then we do the same thing as we go from C to B. We are going from the positive plate to the negative plate. So if Q2 is positive, then there is a potential drop. So that's why we have this Q2 over C2. And the sum of all these potential drops over here, all these potential drops should be 0. So that is how we obtain this equation over here. Well, in fact, basically the physics is over. We are done. No, sorry. The physics is over when we write these two equations also. Then, of course, here we have these three unknowns. We have to relate them somehow. And to relate them, what we do is we just know that the current is nothing but the amount of charge passing per unit amount of time. So if I is, let's say, positive, we know that in a unit amount of time, let's say a charge dq is leaving this Q1, the positive plate of Q1. If dq leaves here, then dq reaches over here. Well, when dq leaves here, Q1 goes to Q1 minus dq. And here, Q2 goes to Q2 minus dq, again, if dq is positive. So that is why we have these minus signs over here. So I is, either I can say it's the negative of the time derivative of the first capacitor or negative of the time derivative of the second capacitor over here. So, and then I have these equations. I have three unknowns and three equations. Now the physics is over. The next is just we need to solve these equations somehow. Well, these equations, I can of course replace this I over here with dq1 by dt, but that's kind of not so useful because I'm still left with two unknowns, Q1 and Q2, which I should somehow relate. So rather than doing that, I just take the time derivatives of this equation, which gives me an equation in terms of the time derivative of I and the time derivatives of these Q1 and Q2, which are themselves I, the current. So if I take the time derivative, This is what I obtain. And if I just use these results, the second and the third equation that I derived, I obtain an equation for the current as a function of time. And if I solve that equation, this is what I obtain for the time dependence of the current. Well, if you know the current, then you can calculate the power dissipated by the current, the power of the resistor. If you know the power of the resistor, you can calculate the total energy dissipated by the resistor. And see if that energy dissipated by the resistor makes up for the difference between the initial potential energy stored in one capacitor and the final potential energy stored in both of the capacitors. And so if the energy dissipated is equal to that difference, then you prove his hypothesis. Okay, we know the current. The next thing is, how about the charges in the capacitors? You might be interested in the charges in the capacitors. Well, we know how the current is related to the charges. We just took one of them. So this is the equation we have. What I did was a trick. I integrated both sides over time from some at t equal to 0 to the final time t. Now, why I did that? Well, this is the left-hand side is the integral of a total derivative. I can integrate it. It just gives me the q1 at the time t minus q1 at time t equal to 0, the left-hand side. Well, the right-hand side, it's an exponential function, which is easy to evaluate the integral. If you evaluate the integral of this exponent, this is what I did. So this is what q1 is. But the equation satisfied by q2 is also identical. Here, instead of q1, you can just put q2. And you have the same equation, same derivation. The only difference will be its value at t equal to 0 might be different. So that gives you, this is your q2. Now, in your first homework problem, you were given that the charge of the first capacitor at t equal to 0 is, let's say, q1. The charge of the second capacitor, which is at t equal to 0, which is q2 0, that is 0. That is what you were given as your initial conditions. And then since you already know these, well, the only thing that is left is, how about this I0? What is that I0? We still need to determine one of those unknowns. I didn't tell you, I don't need to tell you what the initial current is. I can just give you two capacitors and tell you to connect them. You can connect them. I tell you that one of them has this charge, the other one has 0 charge initially. So you have all the information that should be enough to determine what the charges are at a subsequent time. You have to be able to find what this I0 is. Now let's try to determine what that I0 is. You see, our solutions should satisfy this equation still. Now we have determined q1 and q2. If you just put it over here, q1 0 over c1 plus q2 0 over c2 plus I0 times tau times e to power minus t over tau minus 1 times 1 over c1 plus 1 over c2. This is the left-hand side. It should be equal to I times R. Well, I, we already calculated it. I is over I0 times e to power minus t over tau. So these q10, q20, those are things that we can fix initially. We can fix them arbitrarily. So this equation should give us what that I0 is. But let's see. This is our 1 over C equivalent. And remember, tau is R times C equivalent. So if I cancel this C equivalence over here, what is left is R. Tau over C equivalent is just R. Now here I have I0 times R times e to power minus t over tau. On the right-hand side, I have R times I0 times e to power minus t over tau. So they just cancel each other. And I am left with Q10 over C1 plus Q20 over C2 minus I0 times R. This should be equal to 0. Or Q10 over C1 plus Q20 over C2. This should be equal to I0 times R. And this is your I0. Well, we could have done another thing rather than just taking our solutions, putting it in our equations. We have this equation. This equation should be satisfied at all times, including at time t equal to 0. If you write this equation at time t equal to 0, Q1 is Q10, Q2 is Q20, I is equal to I0. It is this equation over here. So in terms of given unknowns, Q10, Q20, this is what's your I0. You see, by the way, this is V1, the potential across my first capacitor. This is V2, the potential difference across my second capacitor. V1 plus V2 is nothing but the potential difference across both of my capacitors. That is the potential difference between this point and this point. So that difference should be nothing but I times R. Yes, any questions? Okay, yes. Well, look at here. I have I0 times R times e to power minus t over tau. On the right-hand side, I also have the same term. I0 times R times the same exponent. I have the same term on the left and the same term on the right. So they cancel. Okay, see you on Wednesday.